Here we have example 2C2 from the book, and here's the figure shown where we have point O, point A, point B, and point D, and we have links from each other from O to A to B, and B to D, and these have links of L and 2L, and given we have angular velocity from O to A, counterclockwise motion at a constant speed, and then we have the given lengths of L. And in this question, we want to find angular velocity of A slash B, angular velocity of B slash D, then angular acceleration of A slash B, and angular acceleration of B slash D. For part A, we want to start out by finding angular acceleration of the links from A to B. So to find this one, we can start off by drawing the velocities of dB and OA and finding which directions they go. And after that, we can find the perpendicular lines to find the instant center. And we can find an instant center if they line up at all, but as they are parallel, they're infinite. And that means there is no instant center, therefore angular acceleration would be 0 for this part A. Moving on to part B, we're going to find the velocity of A by using the two sections in link OA. So we have the velocity of O equals the velocity of A plus angular velocity of O slash A cross the distance between O and A. So moving on from this, we know velocity of O is 0 because it's an instant center. We're finding VA, and we have angular velocity, which is in the K direction, cross negative LJ. So doing the cross product, we can find that covering this up, we can have negative L times angular velocity of OA, and it's also negative, so it cancels out and makes L times angular velocity of OA in the I direction. So moving this down, we move over velocity of A into the other side, and it's equal to L times angular velocity of OA in the I direction. So simplifying this, VA equals negative L times angular velocity of OA in the J direction, and there's nothing in the I direction, there's nothing in the J direction. Moving on to the finding velocity of B, we have VA equals VB plus the angular velocity of A slash B cross RA slash B. And we know angular velocity of A slash B is 0 from earlier. So moving on, we can cross this out, and we have VA equals to VB. And as shown, we can just translate what we found earlier to VB. Moving on to link DB, we can find that VD equals VB plus angular velocity of D slash B cross R D slash B. So we know D is an instant center, so velocity of D will become 0. And then we can plug in VB from earlier for this part. And then we have angular velocity in the K direction cross 0I minus 2LJ. We can do the cross product here and find it equals 0 minus negative 2L times angular velocity of dB. And then we can simplify this to make 2L times angular velocity of dB. So moving this on over to the other side, where the 0 was, we have L of angular velocity O slash A equals to 2L times angular velocity of dB. So we can simplify this and divide this side minus over 2L. So we find angular velocity of dB is equal to L times angular velocity of OA over 2L. And we can simplify that again just to get angular velocity of OA over 2. Moving on to finding angular acceleration, we want to start with finding the normal accelerations too. So first we're going to start off with link OA, where acceleration of O is equal to acceleration of A minus the scalar of angular velocity of O to A squared times the distance from O to A, plus angular acceleration cross the distance from O to A. We know acceleration of AB is 0 since the angular velocity is always constant. So moving down, we have 0 equals acceleration of A minus angular velocity of O to A squared times the distance, which is negative LJ. So simplifying it down, we can move A to the other side, have negative acceleration of A equals to 0I minus omega OA squared times negative L. And then simplifying this, we can have acceleration of A equals 0I minus L times omega O to A squared J. So next we want to find the acceleration of B, and we start off with link B to A. So we have acceleration of B equals acceleration of A minus angular velocity of beta a squared times the distance from beta a plus angular acceleration from beta a cross the distance from beta a. So we know angular velocity from beta a is 0 from earlier. So moving down, we have acceleration of b equals to 0I minus L times omega a squared plus the angular acceleration from beta a in the k direction cross 2Li plus Lj. And doing the cross product here, we can find that the answer is negative L times angular acceleration of AB plus 2L times angular acceleration of AB. So simplifying that down and moving it together, we have acceleration of b equals to negative L times angular acceleration of AB in the I direction plus negative L times omega OA squared plus 2L times angular acceleration AB all together in the J direction. So moving down, we want to look at link D to B. We can have acceleration of D equals acceleration of B equals negative angular velocity of bd squared times distance from b to d plus the angular acceleration of b to d cross the distance from b to d. We know acceleration of d is 0 since it's at an instant center. So moving down, we have 0 equals ab minus angular velocity of bd squared times 2l in the j direction plus angular acceleration in the k direction cross 0i plus 2lj. And from doing the cross product, we can find that it equals negative 2L times angular acceleration of BD in the I direction. So moving AB to the other side, we have negative acceleration of B equals to negative 2L times acceleration of BD in the I direction plus negative angular velocity in the BD squared times 2L in the J direction. And simplifying this down, we have acceleration of B equals 2L times angular acceleration of BD in the I direction plus angular velocity of bd squared times 2l in the j direction. Now, using the two equations for acceleration of b, we can compare them in both their directions. So starting with j, we have negative L times angular velocity of OA squared plus 2L times angular acceleration of AB equals to angular velocity of BD squared times 2L. So getting angular acceleration on one side, we want to move on to the other side. So we have 2L times angular acceleration AB equals to angular velocity squared times 2L plus L times angular velocity of OA squared. So dividing this all, we can find angular acceleration of AB equals to angular velocity of BD squared times 2L plus L times angular velocity of OA squared, all divided by 2L, and that'll find you part C for angular acceleration of AB. Moving on to the I component, we have negative L times angular acceleration of AB equals to 2L times angular acceleration of BD. Because we just found angular acceleration of AB earlier, you can just move this over and have angular acceleration of BD equals to negative L times angular acceleration of AB over 2L. And then you can simplify this down to make it negative angular acceleration of AB over 2, and that will find you D.